Okay, with these preparations, we are ready to state and prove another theorem about when an isometry becomes affine. This theorem states that every isometry from a normed space into a strictly convex normed space is affine. And now let us prove this. This proof will be much simpler than the Mazur-Ulam theorem. Let f from E to F be an isometry between normed spaces with F strictly convex. To show that F is affine, it suffices by the proposition number 3 to show that F preserves the middle point of any line segment. To this end, let us consider the following 4 spheres. S sub A, which is a sphere in E, centered at A with radius the norm of A minus B divided by 2. And similarly, S sub B is the one centered at B with the same radius. Correspondingly, there's a S sub FA in F. Now let us use another letter Y to denote elements in it. This is a sphere centered at F of A with radius norm of F of A minus F of B divided by 2. Note that because F is an isometry, this guy will be actually equal to this. But to avoid confusion to some of you, let me not write that. And similarly, S sub F of B will be the sphere centered at F of B with radius norm of F of A minus F of B divided by 2. That's it. That is the 4 spheres that we will be considering. And now, since F is an isometry, F of SA is contained in S sub F of A, and the F of SB is contained in S sub FB. And let us quickly check this. For any Y, which is F of X, that is in F of S sub A, for some X in SA, we'll show that this Y must be in S sub FA. To this end, we're going to look at Y minus F of A, which is F of X minus F of A. Since F is an isometry, this guy will be equal to the norm of X minus A, which is half of the norm of B minus A. This is because X is in S sub A, but the definition of S sub A Since S of A has radius half of B minus A, x to the center is equal to half of norm of B minus A. And by the isometry again, this will be equal to the norm of f of B minus the norm of f of A. So this proves that y is in S sub fa, and thus we have this containment, and similarly we have this containment. So what does those two containments tell us? Let us draw a picture. Suppose the left sphere is S sub A and the right sphere is S sub B, centered at A and B respectively, which are mapped into S sub Fa and S sub Fb respectively by F. Let us first look at the middle point of the line segment from A to B. This point, A plus B divided by 2. You can easily see that this point is in the intersection of those two spheres. So because A plus B divided by 2 is inside this intersection, we have f A plus B divided by 2 is inside S sub f of A intersection S sub f of B. On the other hand, f of A plus f of B divided by 2 is also in the intersection of those two target spheres. And remember, our goal is to show that this guy is equal to this. So now let us make our claim. Claim f of A plus B divided by 2 is equal to f of A plus f of B divided by 2. To prove this claim, we are going to invoke the definition number 2 of the strict convexity. Indeed, suppose that they are not equal, then by the definition, number 2 of strict convexity, we have for any alpha greater than 0, less than 1, x sub alpha defined to be the convex linear combination alpha times the first guy plus 1 minus alpha times the second guy must satisfy that the distance from x sub alpha to f of A must be strictly less than the norm of fa minus f of B divided by 2, and the norm of x sub alpha minus f of B is also strictly less than the same thing. So some of you might get confused at this point why we have those two strict inequalities from the definition number 2 of the strict convexity. Let me explain those two inequalities. To this end, we need to recall our definition number 2. Give those two inequalities labels. Call this inequality 1 and call this inequality 2. To get the inequality 1, we will take x to be f of a plus b divided by 2 minus f of a divided by its norm. The norm of this guy will be equal to this due to the fact that f is an isometry. Actually, the denominator will be same as the norm of a minus b divided by 2. And we'll take y to be f of a plus f of b divided by 2 minus f of a divided by the same denominator. And we plug in x and y into the definition number 2. And by definition number 2, we'll get precisely the inequality number 1. Here, x is not equal to y because we assumed that f of a plus b divided by 2 is not equal to f of a plus f of b divided by 2. So they cannot be equal. And the norm of x is equal to 1 because, as I explained, the norm of numerator by the fact that f is an isometry will be equal to a minus b divided by 2's norm, which is a norm of the denominator, again, by the fact that f is an isometry. So this verifies the inequality number 1. And the inequality number 2 is obtained by simply replacing f of a here by f of b. So, what does inequalities 1 and 2 tell us? The inequalities 1 and 2, together with the triangular inequality applied on the left-hand side, will tell us that the norm of f of a minus f of b by the triangular inequality is less than x of alpha minus f of a plus x of alpha minus f of b. And this, by the inequalities 1 and 2, will be strictly less than half of norm of f of a minus f of b plus half of f of a minus f of b. So we get the contradiction. This contradiction is due to all the way back to our assumption that f of a plus b divided by 2 is not equal to half of f of a plus f of b. And this proves our claim by contradiction. So this proves our claim as well as the theorem. That's a proposition number 3 above. So we are done.